This video we're going to tackle question 21 on page 159, and this is the combined gas law. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. And if we had constant temperature, you'd have Boyle's law, P1 V1 equals P2 V2. If you had constant pressure, then it'd be Charles' law, V1 over T1 equals V2 over T2. They've combined the two laws to come up with the combined gas law, and we can see that if the volume was constant, P1 over T1 equals P2 over T2. In this case, the question says a cylinder of helium gas has a volume of 1.0 liters, and it exerts a pressure of 800 kilopascals at 30 degrees Celsius. Anytime I'm doing a gas law calculation, I need to change that to Kelvin. So that's 303 Kelvin. And then it says, what volume would this gas occupy at SATP? Well, SATP is listed back here as just down way at the bottom. I don't know if you can see that or not, but it's 298.15 Kelvin, so 298.15 Kelvin, and a pressure of 100.00 kilopascals. And so now I've got all of the values to fill this in. Anytime I'm doing a question, I am going to rearrange my formula and then substitute in. So I use my V2 equals, so if I'm solving for V2, I need to bring T2 to this side and P2 to this side. So it's going to be P1 V1 over T1, and then T2 goes up here, and my P2 comes down here. I'm going to fill this in, and so I've got 1.0 liters times V1 times P1, 800 kilopascals, times T2, so 298.15 Kelvin, over T1, which is 303 Kelvin, and the P2 of 100.00 kPa. Now, there are a few things going on here. I've got Kelvin in the denominator and the numerator. I have kilopascals in the numerator and denominator. They cancel out. It's going to leave me with liters. I also only have two significant digits for 1.0 liters, so my answer should be in two significant digits only. It's my least accurate number. This zero counts because it's at the end of the number, so it's a trailing zeros count for significant digits, but zeros in front don't. So this number is actually 5 significant digits. My V2, I'm going to put this into my calculator, but from a calculator point of view, I need to put those things inside brackets. All these brackets that I've got here are just showing that these are all being multiplied, and I'm multiplying these numbers, but I need to multiply both these numbers if I'm going to divide that. So when I put this into my calculator, I'm going to put 1.0 times 800 times 298.15 divided by bracket 303 times 100.00, and it gives me a value of 7.87, but I only want two significant digits. So my V2 is going to be 7.9 liters, because my units were in liters here. It's going to give me liters as units. Now, for people who are having difficulty with their calculator, one way you can try to deal with that, if you're not sure when to use the brackets, is you can do it like this. So I've got entered this, times this, then I'm dividing by this number and dividing by this number. So if I didn't put brackets around these numbers, I need to divide by 303 and divide by 100. So it gives me the same number. If instead, if I did it the incorrect way, if I said 1.0 times 800 times 298.15 divided by 303 times 100.00, I come out with a wildly different number, because what I'm actually doing is not dividing by this value, but I'm actually multiplying. So hopefully that helps you with some combined gas law. We will do one more question with combined gas law in a second video. In this one, we're going to deal with temperature, so it's a different rearrangement. Check the other video if you're curious.